Today we'll continue with the 8086 instruction set. The basic instruction set format of an 8086 microprocessor. Uh, there will be a mnemonic, there will be a destination operand, there will be a source operand. So this is the format of an 8086 instruction. I give an example here, as you can see here. The this mnemonic here is a move. Move is a mnemonic, and source operand is BL and destination operand is AL. So this are operand is nothing but a type of a field that we put. Either it can be a memory, or it can be a register, or it can be a direct address, or literally it can be even some number. So type of the instruction that can be classified is the data transfer, arithmetic, logical, and program execution transfer instruction, and there are some miscellaneous instruction also. So we have to study the instruction set of 8086 to do the programming. So each instructions will be covered now. So starting from data transfer instruction, then we'll move on to arithmetic instruction, then logical instructions, where will be in arithmetic we'll see with addition, subtraction, multiplication. Logical is logical operation, bitwise OR operation, AND operation, and program float control instructions will have branch looping instructions. So and miscellaneous instruction also we will see in instruction, so that you can write a program for 8086. Now first instruction that we see, the data transfer instruction. So the data transfer instruction is the one which where the transfer of the data from source operand to destination operand. So a move instruction, MOV, is a mnemonic for a move instruction. So a move instruction copies a word or a byte data from a specified source operand to a destination operand. So we have a format for a move instruction. So move followed by a destination and source operand. So that's what the move instruction is. So you can have a register, memory, any operand, but there are some rules. Some combinations are not possible. We'll see what are the combinations. So data transfer instruction is, see, you can move a register with the 16-bit value. You can transfer the data between two registers. You can do a transfer which can be 8 or 16-bit. So here is an instruction where we are moving a value 037A to CX register, and also I can move a data from a memory. So this is a direct addressing I am using, 437AH direct addressing. The data is moved from this location to BL, and then this is an indirect addressing, again a data transfer. So BX is taken as a index register, base register. So it is a base addressing mode, indirect addressing mode. So BX, content of the BX is taken as a memory pointer, and the value stored in that location is transferred to DL register. Another instruction is segment movement. You cannot have a data transfer between two segments. It has to be through a general purpose register. Similarly, from a register to a memory location. So these are the possibilities of move instructions. Okay. So it's a very simple instruction that we can use in most of the programming. We have to go for a data transfer instruction where we need to do some transfer of data between the registers, between the memory location. But at any point, there is no possible instruction that you can use for memory to memory. So like between two memory location, I cannot have a straight away instruction with the move. It has to be through a registers. So let's see another instruction called push instruction. Push is also a data transfer instruction which copies a word from a specified source location to a segment in a using the stack pointer. So it copies the content of a register onto the stack. So that's what the push instruction. So none of the data transfer instructions will affect the flag. So that's the one of the. Similarly, we have a pop instructions. So pop to copy the data from stat stack segment. it will copy the data from the stack segment. Whatever content is pushed onto the stack, it can be retrieved back using pop instructions. So there is a format in which how the push and pop instruction work. So working of a push instruction. What happens when a push instruction executes? So initially, whenever you push a data word, okay, so always push instruction in 8086 is a word data. You cannot push a byte data onto the stack. It has to be a 16-bit operand. So pushing a AX register, BX register, or a memory location content which is 16-bit. What happens? The higher byte of the data is pushed onto SP minus 1. That means stack pointer is automatically decremented. It is not decremented, it is pointed to SP minus 1. Data is saved. Then the lower byte is pointed to SP minus 2. Data is stored. And then stack pointer decrements by 2. So this is the operation. So in another case, let's say pop operation. How the pop operation works? So a lower data byte will be copied from the SP. First it will copy from the SP, and then the data will be copied from SP plus 1, and then the stack pointer is incremented by 2. So this is what happens with the pop instruction. So these two procedures you need to remember, because this is the most frequently asked question, like the working of a push and pop instruction. So probably you need to remember these operation, like which in what way the push and pop instructions work. So this is about a push and pop instruction. Now possibility of push and pop. Push bx, how it will be. So it decrements the stack by 2 and copies bx to the stack. So similarly push ds, and similarly push some value. So every time the value will be 16-bit value will be loaded to the stack pointer. So now we have a pop instructions. So pop instruction is uh, pop pop the value. It will take back the content from the stack. It will take back the content from the top of the stack, and later it increments the stack pointer by 2. So that's how the pop instructions work. So pop dx, pop ds, or pop memory content can also be popped similar to the push instructions. So we need to you can also demonstrate the C, the content in which way this works. So what we can do is we can have a simple simulator here, so that I can demonstrate in which way this works. So you can have this is an 8086 simulator. You can download it in the internet. So it is move al ax comma say 1234h. Then you have push ax. Okay. So once you do this, you can see how the working is going to be. Then you can have an instruction to check what way it executes. So let me execute a single step here. So see here, push AX. So it is going to push onto the stack where SP is this. SP is this. So and when you execute this, it will be executed. So FFFE is decremented by 2 and it becomes like this. And the content will be saved in the stack segment, that is 70700. So you can check the memory window, and you can verify how exactly stack pointer is saved. So you can just go to this memory window. So yes. Yeah, I can just yes, memory. Yeah, we can check it here once in the memory. 1 second. Yes. So you can check it here in the memory. The memory is 700, and I need to check it in the location, that is FFFC. Let me check it. See, FFFC will be having the content 34 and 2. So lower byte is pushed, then the higher byte is pushed onto the stack with the decremented. So you can see the content saved in the stack. So this is how the stack pointer changes the value whenever push and pop instruction is executed. So now going back to the PPT. So this is how the push and pop instruction works. I have shown the push instruction. So there are string manipulation instructions. So I think these string manipulation instructions you can concentrate just by looking at the mnemonics. I don't want to elaborate much here. So we can move further with an LEA instruction, which is load effective address, and which loads the address to a registers if you want. So if you want to load address value to BX register, you can use LEA instructions. So similarly, if you want to load the address of BX plus DI, effective address of BX and DI together, so base and index, then you can use in this format LEA CX BX DI. So it will load addition value of BX and DX to CX register. So that's how this LEA instruction works. Similarly, LDS instructions. So the LDS instruction is register comma memory. So you can load the address of a data segment register as well as the register mentioned in the instruction from a memory. So as you can see in example here, LDS BX comma 432X. So it copies the content of the memory at displacement 432X, that is content from 432X, to the BL and next content to BH. Then consecutive locations thereafter to DS register. Two locations you can see here. It copies the content 16-bit value from 432X onwards to BX register. Then 4328 onwards to DS register. That's how you can load a segment register and BX register. Basically, it helps to point the different uh, the segments. I can address different segments. And LES instruction is register comma memory. So LES DI comma an operand. So you can put an memory operand from where you want that memory values to be loaded. You can specify to DI register and extra segment. So this is an LES instruction format. Now let's move on to addition instruction. So add with carry, the same usual addition with the source and destination. And as you know that flags are affected using add instructions. Then for an example, if you want to consider add AL comma 74. So we are adding register AL with 74, and result will be saved in AL register. Then add with carry CL comma BL. We are adding CL and BL register. Then content will be saved in CL register. Similarly, add BX comma DX and adding a DX comma SI. So these are all the possibilities of add instructions. So basically, you can have direct, indirect, register, immediate. All addressing modes are possible with add instructions. There is another instruction which is increment. Increment instructions. Increment instructions. You can have for incrementing a specified memory. You can increment or decrement. So again, increment BL can be used here. Yeah. So increment instruction basically it increments the BL register content or CX register, whichever register you specify in the memory or a register, it can be incremented by one value. So as you remember one thing, see the note here, the AF, overflow, parity, fine flag, zero flag are updated, but carry flag is not updated. So the carry flag is not affected using increment instruction. Subtraction instruction is again similar to addition, but only thing is uh, source is subtracted. So add subtract AL comma BL, then AL minus BL is destination is subtracted uh, with the source, and the value is saved in the destination register. So again flags will be affected. So similarly subtraction, after that you have decrement, again similar to opposite to the increment instruction, value will be decremented by 1 here. Then you have an instruction called DAA, decimal adjust after addition, and DAS, decimal adjust after BCD subtraction. So this is again an important instruction that you can have. So DAA and DAS. So basically this instruction can be used whenever you use a BCD arithmetic. For example, if you consider an instruction wherein say for example you want to add two BCD number, let's say the number as 36H and move BL comma uh, take it as 46H. Now if I am going to add AL comma BL, so you know that the answer is going to be hex addition, but we need in decimal format. So for that I will execute DAA. Okay. See, if I am using this instruction, so this DAA makes me uh, adjust the result such that I get the value instead of 36 plus 46, my answer should be 82. Correct? So this is an answer. 36 plus 46, answer is 82. Whereas here in hex addition, I get 36 plus 46 as 7C. See, this is the difference. So in a usual addition in hexadecimal format and a decimal addition. So when you go for a decimal arithmetic, I want the result to be in decimal. But in any computers, you take a microprocessor, microcontroller, the additions, subtraction, everything is in hexadecimal format. So you should have a separate decimal arithmetic to take care of these things. So for that reason, we use this DAA instructions. So after addition, depending on the status of the flag, it will adjust the result to 82. Okay, so that's the basic. So remember, it has to be used when before using a pure decimal number. So That's the one thing you remember. Say I cannot have here a number like f6. So I cannot expect f6 plus 36 to be added and I want result to be in decimal. No, because f6 is not a BCD number. It is a hexadecimal number. So this has to be a BCD number which is a combination of 0 to 9. Then only you can have this kind of instruction format like using DAA. Similarly, when you go for DAS, again similar thing you can perform. You want to subtract two numbers, let's say move AL comma 90 H and move BL comma 44 H. Then let's say I want to subtract AL comma BL and I want the answer to be in decimal. Then this has to be the instructions. So to see this, simulate this instruction, we can simulate it here. So just to go back to the original instruction and just check it once, see how it shows. That is single step execution. See here 36 is loaded, 46 is loaded, and you carefully see after addition I get answer as 7C. See here 7C is the answer, which is not the BCD number. Once again you do DAA, it becomes 82. See how that 36 and 46 has adjusted to 82 with the DAA. Similarly, we have this 90 and 44. So 90 and 44 I am going to subtract. I am going to subtract the value, subtract AL comma BL I will do. The answer is 4C. But actual answer is how much for the DAS instruction. So I am subtracting 90 minus 44. I should get 30, sorry, 46 as the answer. Okay. So I think, yeah, 46 should be the answer. See here, DAS makes it 46. So this is how the DAS works. So this is the importance of a decimal adjust instruction in addition as well as subtraction. So let's move on to the basic again. So this is the two instruction that has most used DAA and DAS instructions. So one for addition, one for subtraction. Now let's go with the multiplication. So I think this multiplication, normally there are 8-bit multiplication possible, 16-bit multiplication also possible. So when you go for an 8-bit multiplication, the answer will be stored in AH and AL register. When you perform 16-bit multiplication, answer will be stored in DX and AX. See, the idea is this multiplication, there will be only one operand like mul CL register. Then the other operand is always by default AX register. Okay, the AX register is a fixed operand. The other register you can choose what you want to multiply. So depending on the size, whether you perform 8-bit multiplication or a 16-bit multiplication, the result will be saved accordingly in a fixed location like AHAL or DXAX as shown here. Then flag registers will be affected as usual. See the example. Mul BH. When you perform mul BH, what and all will be multiplied? It is AL with BH always. AL is a default if it is a 8-bit register. See here, BH is a 8-bit, so it is multiplication will be performed with AL only. In the next example, you see it is CX, mul CX. So it is a 16-bit. So other is also going to be 16-bit, which is AX. And the result will be saved in DXAX. It will be DXAX. Now, mul byte PTR, you can also take a byte location from a memory and that can be multiplied with the AX, and you can also take a so See here, I'm going to perform the multiplication mul BL. Now you see the content, what happens here. So the content, yes, now content becomes 0E C4. See this value, 0E C4 is a value, 0E C4, which is the AX register content. So I am multiplying AL with BL, content will be saved in AX. Similarly, if you go, AX is now loaded with 1, 2, 3, 4. I am multiplying with the BX, which is 002. See, 002. See, I am actually doubling this value. Multiplying this means doubling. So that means I will multiply this, so value has to be dx ax. Now see, dx will be this, ax is going to be this. So this is what is the multiplication of a 16-bit into 16-bit. Now moving back to the PPT, there is a division instructions. Again, it divides the number whatever you specify by AL or AX. So I can divide a number by AL or AX. The result will be saved in a similar way. As you can see, AX register, the divisor is in the register or memory location. A will contain the 8-bit quotient and H will contain the remainder when it is a 8-bit division. If it is a 32-bit division, then dx ax by ax, the dx contains the remainder, ax contains the quotient. So this is what the division. So it's a very simple, similar way as for the division is concerned. So so these are few major instructions that we need to go through. So now further instructions on this will be basically program flow control instructions and some of the arithmetic and logical instructions also there, which will be covering up later. So